Section: Introduction. In this section, we examine how large language models, LLMs, can benefit from in-context learning to improve their ability to follow instructions. We explore the concept of in-context alignment, where providing just a few question-answer pairs in the prompt can help base models interact with users effectively. This method offers a simple and flexible way to customize base models without changing their weights. Our evaluation focuses on the URIAL prompt strategy across various base models, such as GPT-4 base, using established benchmarks like MT-Bench and Alpaca Eval 2.0. While URIAL shows promising performance, it still falls short compared to instruction fine-tuned models. To enhance URIAL, we investigate strategies like incorporating many-shot in-context learning with high-quality demonstrations. However, adding more examples only leads to limited improvements. We then introduce a greedy algorithm to select in-context examples that optimize the MT-Bench score, nearly bridging the performance gap with instruction fine-tuned models. Furthermore, we emphasize the importance of providing correct question-answer pairs for effective in-context learning in instruction following tasks. Adding incorrect demonstrations can actually harm model performance. Our work offers a more detailed understanding of in-context learning as an alignment technique compared to previous studies. We compare the performance of base models using the URIAL prompt with their instruction fine-tuned versions on the MT-Bench benchmark. While base models with URIAL perform competitively on the first turn score, they struggle to match the performance of instruction-tuned models, especially in the second turn score due to the lack of multi-turn demonstrations. Therefore, we focus on single-round conversations in our analysis. We delve into exploring ways to narrow the performance gap between in-context learning and fine-tuning on instruction following tasks, particularly focusing on Mistral 7 BV0.2. By experimenting with different selection criteria for adding demonstrations, such as random examples and diverse instructions, we aim to improve the MT-Bench score. A greedy search approach proves effective in maximizing the MT-Bench score by sequentially adding high-quality instructions to the URIAL prompt, almost reaching the performance of instruction fine-tuned models. Our findings suggest that simply increasing the number of in-context learning examples is not enough to consistently enhance instruction following performance. However, a strategic greedy search approach can help bridge the performance gap with fine-tuned models. Section Summary. In this section, we explore the concept of in-context learning, ICL, for aligning large language models, LLMs, with instructions. By incorporating just 3 carefully selected question-answer pairs in the prompt, base models can effectively follow instructions and engage with users at a level comparable to instruction fine-tuned models. Our evaluation of the URIAL prompt strategy across various base models reveals that while URIAL performs reasonably well, it still falls short of instruction fine-tuned models, prompting us to investigate strategies like many-shot ICL and a greedy algorithm for selecting in-context examples to enhance performance. Section: Understanding ICL for instruction following. In this section, we delve deeper into the challenges of using in-context learning, ICL, for instruction following. We highlight the importance of matching questions and answers for effective demonstrations within a context. Our study reveals that even when using demonstrations with random labels, the performance of ICL on tasks like classification and multiple-choice questions is not significantly affected. To further investigate this, we conducted a similar study focusing on instruction following. We tested different configurations using sets of in-context examples, where each example consists of a query x_i and its corresponding correct answer y_i. Initially, we used the original base model without any demonstrations, resulting in poor performance. Surprisingly, providing questions without answers yielded good results. However, when we shuffled the answers so that correct answers were paired with the wrong questions, the performance significantly decreased, especially with more examples. We then experimented by pairing questions with answers from different but related categories, in domain. This approach, although not as effective as using correct answers, still achieved decent scores. Conversely, sampling answers from unrelated categories, out of domain, led to the worst instruction following results. These findings emphasize the importance of using answers with both correct content and style for successful instruction following, especially as the number of examples increases. This highlights the unique nature of ICL for instruction following compared to other tasks. The transferability of in-context examples was also explored, showing mixed results when applied to different base language models. This variability suggests that the effectiveness of ICL demonstrations may vary depending on the pre-training of the base models, potentially explaining differences in performance across models.